Have you ever thought about how you started, how we all started? It's one of the most incredible journeys in biology, that leap from a single fertilized egg to a living, breathing organism. It's like building a skyscraper, but it all follows one surprisingly simple blueprint. Let's get into it.
So that's the big question, right? You start with just one cell. How in the world does it manage to build an entire body with trillions of cells all organized perfectly into tissues and organs? Well, the answer starts with a process that is just visually stunning and honestly beautifully logical. And that first step is a process called cleavage. Now, here's the key. The embryo isn't getting bigger yet. Instead, that one big cell just rapidly divides over and over, making tons of smaller cells. Each of these new smaller cells is called a blastomere. This is literally the first construction phase, turning a tiny blueprint into a real structure. Okay, so here's our game plan. We're going to start with the single most important factor in this whole process, what I'm calling the yolk's golden rule. Then we'll look at the two main strategies embryos use: total and incomplete cleavage. We'll see what they build, this hollow ball, and finish up by looking at the blueprint's very first draft. So what is this master instruction, this one rule that every single developing embryo has to follow? Well, it all comes down to its power source, the yolk. Right, here it is, the golden rule. The amount and location of yolk basically dictates everything that happens next. Think of yolk as the embryo's packed lunch. It's packed with nutrients, which is great, but it's also super dense, which makes it a physical barrier. The source material puts it perfectly: dense accumulations of yolk retard cleavage. It literally gets in the way of cell division. So how an embryo deals with its yolk, that changes the entire game. So let's check out the first strategy. This is what happens when there isn't a crazy amount of yolk in the way, and the embryo can just go ahead and divide the whole egg, top to bottom. This is called total, or holoblastic cleavage, and that name makes sense. Holo means whole. The dividing lines, or furrows, cut completely through the entire egg. You see this in animals that have a pretty manageable amount of yolk, like sea urchins, a cool little creature called amphaxis, and our star for this section, the frog. Now, the frog egg is a fantastic example because it has a moderate amount of yolk, but it's not spread out evenly. It's all packed into one half, called the vegetal hemisphere. The nucleus and the important machinery hang out in the other half, the animal hemisphere. And trust me, this imbalance makes a huge difference. Okay, so you can really see the yolk's influence right here. The first two cuts, they're vertical, slicing right through, no problem. But look at that third division. It's supposed to be horizontal, right through the middle. But it's not. It's pushed way up toward the top because that dense, heavy yolk at the bottom physically gets in the way of the cut. And here's what you get. Because that third cut was off-center, you end up with cells of totally different sizes. You've got these smaller cells on top, the micromeres, and these bigger, yolky cells on the bottom, the macromeres. So yeah, the cleavage was total, it cut all the way through, but it was definitely unequal. And just to make this crystal clear, let's put the frog next to Amphioxus. Amphioxus has just a tiny bit of yolk, and it's spread out nice and evenly. The result? A much cleaner, symmetrical division that creates cells that are all pretty much the same size. See, same general strategy, but a little change in the yolk leads to a very different looking result. Okay, but what happens when the yolk isn't just an obstacle? What if it's a mountain? Well, that brings us to strategy number 2, where the embryo has to get really clever and just work around this massive yolk deposit. Seriously, think about a chicken egg. It's almost all yolk. How is a cell supposed to divide that? The short answer is, it can't. So it has to come up with a completely different plan. This line from the source material just nails it. In animals like birds, reptiles, and fish, all the living, dividing stuff is just this tiny little cap sitting on top of the giant yolk. So the divisions only happen within that cap. The yolk itself, it just sits there, completely undivided. Now, this strategy has two main flavors. The first is what we just talked about, discoidal cleavage. You get a little disc of cells forming on the yolk surface. That's for birds. The second type, found in insects, is even wilder. It's called superficial cleavage. In this case, the nuclei just divide like crazy inside the yolk. Then they all migrate to the outer edge, and only then do the cell walls finally form around them. So strange, right? So after all this frantic dividing, whether it's total, incomplete, equal, or unequal, what do we actually have? Well, the embryo hits its first major milestone, a structure called the blastula. The blastula is basically the finished product of all that cleavage. For a lot of animals, it's a hollow ball made of all those blastomere cells we mentioned. And that empty, fluid-filled space in the middle, that's called the blastocele. Creating this hollow structure is absolutely crucial because it sets the stage for the next, even crazier phase of development. And you can really see our whole story right here. Look how the yolk's golden rule directly shapes the final blastula. In Amphibioxus, with its small, even yolk, you get a nice central cavity. In the frog, that heavy yolk on the bottom pushes the cavity all the way up to the top. And in a bird, the cavity is just a tiny slit between that disk of cells and the massive yolk underneath. It all comes back to eat the yolk. The big takeaway here is that none of this is random. Not at all. The rules of cleavage, which are set entirely by the amount and location of the yolk, directly build the embryo's very first fundamental structure. The first step completely determines the shape of the second. So, we've followed the architect's main rule, and we've successfully built the first draft of our organism. The foundation is laid. So, what happens now? So, let's recap. We've gone from one single cell to this amazing multicellular structure, the blastula. This first draft is officially complete, and it was built from start to finish by following that one simple, elegant instruction, the yolk's golden rule. But this is just the beginning. I mean, a hollow ball of cells is still a long, long way from being a frog or a chicken. The next stage is where things get really dramatic. This simple ball has to twist, turn, fold in on itself, and rearrange in incredible ways to start building something that actually looks like an animal. But how that happens? Well, that's a story for another time.